Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Welcome to Schweitzer Drive. The electric power grid is considered to be the largest machine ever made. From its humble beginnings at Pearl Street Station 145 years ago, this massive network has evolved to meet the growing demands of our modern society. Despite sometimes being described as old and outdated, the U.S. power grid has proven to be remarkably resilient, reliable, and secure. My guests today are SEL Senior Vice President of Sales and Customer Service, Gerardo Urrea, and SEL Vice President of Marketing, Bryan Fazzari. We are going to discuss what's at the heart of the enduring success of the grid and how it continues to power our lives amidst the electrification of everything. Gerardo leads the division that supports customers worldwide with SEL technologies and solutions. Since joining SEL in 2003, he has held various roles, including Protection Design Engineer, SNCS Business Director, Regional Sales and Service Director, and Vice President of SNCS. Gerardo holds a bachelor's degree in electrical engineering from the Technological Institute of Hermosillo. Bryan leads our global strategy, promotion, visibility, events, and technical education. Bryan has held various roles in R&D and SEL's engineering services group, including automation group manager. Bryan received his BS from the University of Idaho and is a member of IEEE and PES. Welcome, fellas. First, I want to set the stage for our discussion. I've noticed that in articles and media stories, there is this perception that the power grid is outdated and cobbled together. Here's a few recent examples of headlines to illustrate this point. Creaky U.S. power grid threatens progress on renewables and EVs, from Reuters. America leans on aging power plants to fend off electricity shortages, Wall Street Journal. The aging U.S. power grid is about to get a jolt, Wall Street Journal. The reality is the average U.S. customer loses power less than 2 times per year for a total of less than 5 hours, which represents 99.95% reliability. And, I was just talking to our Dominion friends. Their reliability is 99.999, so very reliable power systems. While there have been some notable outages and blackouts, when you consider the 145-year history, the U.S. power grid has shown remarkable reliability and resilience. Will you talk about some of the design features and technologies that have contributed to this success? Gerardo, let's start with you.
I think when the power system was created at the beginning, many considerations were taken to have a very robust and reliable system, building redundancy systems to be resilient. So I think that was at the beginning and helped us to build these systems very robust and reliable. Also, I think having backup reserve of power help us as well to have different paths for transmission lines for different power plants to be able to distribute power across the country, and that help us to keep the system very robust and reliable.
That's interesting you bring that up because if we look back, well, certainly before any of us got into this industry, utilities would self-organize and create reliability councils. That's how the WEC started out here in the West, where you'd get the Washington Water Powers or the Puget Sound Energies or the Idaho Powers to get together to cooperate to provide reliable power. If we had to take a generation site offline, the Idaho Power and others to provide electricity while that particular resource was out. And then while they call it a grid, I don't think the electric network is really set up in this, XY configuration. Rather, it is a system of interconnected wires. And our industry, I think, has always done a good job of figuring out how to organize the grid, if you will, if we're going to use that term, to provide reliable electricity, even in the event of a contingency like a fault or even sometimes, multiple contingencies. Bryan, what are your thoughts then?
You introduced it originally when you were starting this episode as one of the most, maybe the most complex machine that's ever been built by anyone, anywhere, at any time in history. And you just described that as also one of its greatest features. I think what a lot of people don't realize is the grid truly does interconnect many different sources of generation. We are so connected. When we flip on that light switch, you've got electrons coming from hydroelectric facilities, from coal-fired power plants, natural gas power plants, this incredible diversity, more variable energy resources every day, all of these things coordinating together to make sure that it stays reliable. So I think the challenge is this is a big machine, but also the benefit is this is a big interconnected machine with a lot of fail-safes and a lot of redundancy designed from the very beginning.
Yeah, that's that is a good point. If we pull a little bit farther on that string, then how has the grid evolved to accommodate new technologies and advancements and increased demand? And maybe stepping back just a second, what are the differences, say, when Edison and Insull, were putting the power system together? It's really what we have. Our model now is the, generation, transmission, distribution systems, all vertically integrated in a utility compared to what we're seeing today. Has it changed very much, or would Edison be surprised if you were to go look at say, I'm looking out the window at a Vistas, which was Washington Water Power? Would he be surprised at how the power system is being operated and controlled? Or would he go, I can see science taking us a little bit farther, but basically, generate energy, transmit it, and then get it to a home or a factory?
Well, I'll put it this way, Dave. When I started my career in CFE, we were not having a lot of communication on our substations. Normally, we're also having people in substation taking care, doing maintenance.
But things seemed to work okay, didn't they?
Yeah. But also, what happened is that many of those relays, in this case for me, were electromechanicals. Mm-hmm. And then we were transitioning, from a first generation of electrostatic relays to digital ones. And that was a way, path to start adding a lot of innovation and replacing all electromechanical relays. That trying to buy one of those relays was very complex and expensive.
What was the driver though? Right, for years and years we used electromechanical relays are still in service today. What was the driver then? What was the motivation for CFE at the time to go from tried and true electromechanical relays to these newer technologies?
Well, first, I think was because many of them start, having trouble to calibrate them or lacking with the personnel capable of doing that. And then the benefits of the new technology.
So without the calibration, you would have misoperations or miscoordinations with relays. So there was a reliability issue you were trying to solve with new technology.
Yes, but also I think the complete benefits, even recording, knowing when my fault happened. I remember going back to my substations and see those flags, on the electromechanical relays, but I never knew when that happened.
So for the audience, if back in the day when there were these electromechanical devices, they'd have these discs, and based on the torques created by how much current was flowing through the coil of these discs or the coils were attached to the disc. There was enough energy going through them. The disc would rotate far enough, and that rotation represented a fault. It would trip the circuit, send a close a contact to trip a circuit breaker, and then it would have basically an orange flag fall saying, hey, I was the relay that called for the trip.
My fault.
Yeah, my fault. But that's the only information you got out of it, right? You didn't know how much current was flowing in the line at the time. Maybe you could deduce it from what the setting was for the disc or something like that. But yeah, that was about it, right? And then now you as the engineer, I guess, are left to scratch your head, and it's like, what caused the fault? How far out is it from the substation and whatnot? And so I guess what you're telling me is because it had an event report in it and it could do a distance calculation, you had all the information to send a crew out 5 miles from the substation on this particular line to go restore power.
Yeah, so my event report will be asking people in the street if they saw something.
That was prior to electromechanical relays. Did you see a flash?
Those electromechanical relays, I mean, like you described, you get a little orange flag that pops up saying, hey, I did something or I saw something, right? I think the analogy a lot of folks would resonate with is, have you ever popped a circuit breaker in your own home, right? You get the little orange flag or the little orange window showing up and you got to reset that circuit breaker. The benefit of that being in your home is that's a very contained little tiny part of the power grid, and you can usually figure out what caused that. We were talking yesterday about a transmission line that connects a lot of the states on the west side of the United States. How long was that? 820 miles or longer? All right. So now you're going to have this transmission of power occurring that's almost 1,000 miles long, and you don't know when something operates. You can't see anything. And to me, that is the benefit. Maybe this is because I have an automation background, but the ability for these devices to record what happened and tell you the story after the fact for the first time, you're able to see what's happening on that 1,000-mile line, which is, I think, a lot bigger challenge than a circuit breaker in somebody's house. That's a long ways.
And also for big, long transmission lines, knowing where the fault happened, right? And being able to send a crew to that precise location was a ton of time saver for us back in those days. So that's something that we, nowadays we get for granted, but it was totally new 20 or 25 years ago for many of the utilities that were transitioned from electromechanical relays to digital ones.
Yeah, and coming back to the why the advancements in technology, utilities, because they want to provide reliable service, have standards and metrics for what reliability should be. We talked about 99.95% that's probably on the lower end of reliability for utilities days. We mentioned that Dominion has 99.999 reliability goals, and many others are the same way. A lot of technology is being deployed in these power systems so that if there is an event, that they can quickly isolate that part of the faulted power system and restore power to keep lights on to as many people as they used to. I remember when I started in the industry that the KD and the safety numbers were important, right? How many hours of outages are the number of outages. And I think those are almost put to the side these days when they're talking. Now they're measuring momentary outages, in terms of seconds and just blips on the power system. That's what utilities are looking at. So it's every time I go out and visit one of our customers, one of the utilities, they are talking about reliability and how do they improve it, and how by adding new technology, more of it throughout, say, in particular distribution systems, that they're vastly improving their reliability numbers and the uptime, if you will, for customers.
I think one of the biggest challenges there is maybe instead of the power grid, we should be calling it the power web or something. The way those distribution networks look, you got to think there is electricity going to everybody's houses. So look at Google Maps, look what that looks like, and the implication there. What you're talking about is be able to improve the ability to deliver power to anywhere on any street at any time from multiple directions, right? So you have an outage on A street and you should be able to reroute power from B street over around that outage. I think the challenge, what's so interesting about being part of this industry, maybe speaking to, is the grid really decrepit or creaky, right? It is so fun to design a solution for something that feels complex. That's a lot of wire. That's a lot of customers. It's a lot of generation that can make that work and improve that resiliency and deliver those results without delivering something so complex that no one knows how to operate it. That's where we're going to get in trouble.
So amongst us three fellows, we've been talking about all of the great things our utility customers doing to improve reliability, and they're improving their numbers. But why do you think there is this perception of frailty? We just mentioned three articles in various news media that are saying it's a fragile network. We're in a world of hurt. It's there's going to be massive blackouts, if you will. Why do you think that happens in the news media, given the I'll argue the phenomenal record that the utilities, certainly in the U.S., from a reliability standpoint, provide and do provide every single day?
Well, I think the public's not aware that all the investment that is being done in the electrical power grid. Mm-hmm. And I think, like we engineers, we're not so good on social media. Probably we don't polish that stuff, but there is so much going on.
This is exactly what we're doing right now.
Exactly. Yeah. So we are trying to improve that. But yeah, I think it's because we do not disclose how much we do in the power grid and how much we continue investing in new technologies and deploying new, cool stuff there.
Yeah, I think a lot of it is a problem of visibility, and in the absence of data, a lot of assumptions get made. So if you flip a light switch, there's this miracle that happens. Those electrons are delivered to you at that moment in time when you need it. But if I'm a member of the general public that has never thought about that, I just assume the lights are going to turn on when I flip that switch. I'm sitting here looking at my smartphone sitting over there. That device that's a beautifully engineered device, and I buy a new one every couple of years. So you compare that with a transmission line that was built in the 60s or 70s or earlier, sitting on a structure that has been there for as long as your parents or your grandparents have lived there. It's easy to start to draw some conclusions about, well, that's been here forever. Surely that's falling apart and needs to be replaced. And I think you're always going to be able to find something that needs to be worked on, right? This is a big machine. It's the biggest machine that's ever been built. But the amount of work going into the electric power grid worldwide is hard to see from the general public. And I think the perspective of, well, I can just throw away and replace all my electronics every couple of years. Why aren't I seeing that elsewhere? You can't do that with a machine that size. It's an incremental improvement, and it's built on top of 100 or more years of work.
I'd pull a little bit on the thread of, should we be concerned about the power system, right? The articles we mentioned do raise the issue of concern. I think I'll put a little bit of engineering behind why we might be concerned. We have a lot of retiring, what we call those spinning mass or spinning reserves, if you will, right? The traditional, whether they're coal fire plants or even to the degree we're not building gas turbines, something that is reliable and dispatchable. It's always on. And we're replacing that with the intermittent resources, whether it's wind or solar or what have you, that are not always there. And then we're trying to couple those with batteries too, so that we have a little bit of storage once we've created with the wind or the solar. And what we've done, the older power systems, say 20 years ago, had a lot of margin with spinning reserves. So say there's 20%. We've slowly, maybe quickly these days, eaten into that spinning reserve, that really reliable dispatchable power, replaced it with the not dispatchable stuff, the intermittent stuff. And so I can see, just from my engineering perspective, this is not, I'm not writing an article to scare people by any means kind of thing, but we do have this challenge. We have politicians or whatever mandating, what kind of generation we can use to produce electricity, and without, I would argue, a full understanding of the engineering impact of those decisions. And I think that's where somebody, at the Wall Street Journal can hear some of that. Maybe they can just inflate it to be really a scary kind of thing, or we don't know what we're doing on that, as engineers building and maintaining power systems. And I think that's kind of how you get into that. Maybe, you pointed we need to get better at social media. Maybe the other thing we need to be able to do is really lay it out so that your mom can understand, what the impacts of these particular decisions. And as a society, if we think that's the way we want to go, we also have to then accept our power systems aren't going to be as reliable, and is that okay, right? And then if it's not, then we have to make some decisions. Should we, we just got done doing a handful of podcast episodes on nuclear, and I'm still convinced we end up at nuclear if we want, dispatchable, non-carbon emitting generation sources that are reliable. The question is, how do you get from now to that nuclear state? And I am convinced that gas is going to have to be a big player in there. I was at a National Association of Manufacturers conference this week, and they had one of the large gas producers talking about it. And he made an interesting statement. I was usually on board with saying, hey, our energy production mix should be all of the above, right? There's going to be hydro and nuclear and gas and solar and wind, and it all made sense. But in my mind, I was thinking it's really going to be hydro and nuclear and gas, and then we'll have a little bit. What the guy from the gas industry was saying, we need to do the best of the above. Mm-hmm. Right. Let's take the stuff that can really make the biggest impact in terms of our reliability, because that's what everybody wants. To your point, Brian, is I want to walk into a room, hit the light switch, and it comes on, and I never want to have to think about it. Right. Never have to think about it.
And one missing point, Dave, there's also the loads are changing. I mean, you're talking about all the generation and how we provide that power to the grid, how the juice is going to flow, but also the loads are changing. We're seeing more EVs being added to the
these mobile loads where they change. They're in one spot of the grid one day or 1 hour, and they're in another part the next hour.
Yeah. So if you walk in the night in any neighborhood, you will see all those transformers, those
humming.
Yeah, but also there is also a big change in our industry in regards of data centers and being a huge energy consumer now with AI. And I think that's also challenging the industry, how we're going to provide that energy for those data centers in all these different locations across the U.S.
Well, let's pull on that, because that was my next question, essentially, is with the electrification of everything from vehicles to homes, the inclusion of these large data centers, right? Ranging, small ones are probably 300 megawatt loads, right? And the bigger ones are over a gigawatt, right? These are huge systems. Just to put that into context, the AP1000, the Westinghouse nuclear, one of those, AP1000 puts out 1.1, 1.2 gigawatts. And we're saying I need to build a nuclear reactor the size of these Vogtle 3 and Vogtle 4s for every one of these big hyperscaler data centers just to provide the power for it. That's almost mind-blowing thinking about it.
And every EV is around, every single one is at least it's 100 kilowatt hour battery.
Mm-hmm.
And you put like the new big F-150 or the new GMC Hummer, those ones are like 250.
It's amazing, right? These are big loads. So with that, how is the grid adapting to meet these new demands, or how, maybe a better way to say it, how does it need to adapt to meet these new demands?
We were checking, I remember, Brian, a few days ago, the duck curve about the load in the power system.
Right.
So real quick for the listeners, the duck curve is you have a big demand in the morning, right, where everybody's getting
breakfast
ready to
time.
go to school or head out to work or whatever, make some coffee. Then nobody's at home, so the power demand goes down, and then everybody comes home at 5 o'clock and wants to cook dinner and wash clothes and everything else. So it kind of looks like a duck and
watch TV.
Yeah,
and
football.
Interestingly, the more photovoltaic, so solar, the more solar we put on the grid, solar peaks from 2 p.m. to 5 p.m., 2 p.m. to 6 p.m. That is the back of the trough of this duck curve. And so you actually get a steepening of this curve where the trough gets real deep. And then as solar starts to drop off, and at the same time, we all come home and start cooking dinner and watch football or whatever it is we're watching. That is an engineering challenge all by itself.
Well, yeah. To explain to my mom is all this solar is producing so much power at exactly the wrong time when I need it. Nobody's home and needs it, right? But I'm pushing so much power back into the grid.
Right. I need it 2 hours later.
And that's going to be the argument for that's when you need a battery, right? So you can store it up from 2 to 3 o'clock and then be able to dump it out of the battery at 5 or 7 o'clock at night.
Well, and I guess that's a great opportunity for us as a industry developers of technology. How can we help to balance that, load and manage the complete changes that are happening in the way that we consume energy, but also the way that we produce energy, adding all these renewables that it's coming, like it or not, and we are seeing that.
Well, so some of the things is how do you change behaviors on what you do? So I guess I could start cooking my dinner at 10 o'clock at night instead of 5 o'clock at night, right? To push the demand load way out and help everybody else. But I don't think my wife is going to go in for that, or my kids will go for that.
It's like going to a conference in Paris. You try to get takeout before 7 p.m. and they're going to tell you to go away. That definitely happened to me a couple months ago.
Yeah, but going back to that topic, I think the challenge for us is going to be how we adapt our technology to help to balance that management of load and generation, and how we help the industry and the utilities to manage the complete power system to have those conditions. And we have great solutions with engineering services to do that.
Let's talk a little bit about that. We've been complaining for the last 15 minutes about, isn't this awful kind of stuff? And the engineer in us wants to go solve a problem, because that's what we love to do as engineers. So how can we ensure the grid continues to evolve and remains a reliable backbone for our increasingly electrified society?
All right. So what are we going to end up with at the end of the day? The transition that we're seeing right now is the retirement of some very large generating facilities and the introduction of many relatively small, comparatively speaking, generation facilities with a lot less inertia and a lot less ability to deal with the unexpected. You got to always assume something's going to happen at some point. Will the grid fall apart when that happens? And so our challenge is to make sure that we have systems in place that can handle that. So I think what you're going to see is the application of a lot more computerized intelligence. So this could be firmware in a protective relay. It could be code in an automation platform or a computer of some kind. But taking that and taking our ever-increasing ability to measure data at a very high rate, because electricity moves at the speed of light, you got to be watching it quick. Things can change fast. You're going to see more and more use of that data to keep that grid that maybe is a little bit more, I don't want to say brittle, but less able to just deal with the unexpected like it was before.
We're going to have to figure out right?
Exactly. So we're going to have to figure out another solution for that. That's going to be very interesting to see. So just the application of information and computational capability is going to be an important, and keeping it as simple as we possibly can.
Yep.
Yeah.
And from our side, how can we help the industry to scale really fast to help them with those challenges, Dave? I think it's a great opportunity. How can we deploy faster the new substations, the new control systems, that's also a great opportunity in the future for all of us.
That's a great point because, I mean, we're talking about you can measure faster, you can get more data. The implication there is you need to install a bunch of devices that can give you that data. And how do you maintain those? How do you keep track of those? How do you keep them cyber secure? They're going to be a target by all kinds of folks for all kinds of reasons. There's a big challenge there.
What do you guys see as particular technologies that can enhance the grid's reliability or dependability?
The first thing that comes to my mind is time domain for all these IBRs or...
Why is that? Why time domain versus, say, perhaps traditional ways we've used to monitor and control the power system?
We have seen, not only in the U.S., but all across the world, when you have a big, IBR or a renewable power system or power plant with no inertia at all, or common protection doesn't react properly to that. It's all about, the source. With time domain, it's all about the fault. And that's where we see a huge benefit for that technology and help the utilities to trip really fast to identify those faults instead of, not operating at all.
Just to try to explain that as simply as possible, here's an example. So imagine your electric utility provides you power generally day to day, but the grocery store you go to every week has a large generator that they run all the time. If a fault happens, that the energy feeding that fault is going to come some from the utility and some from that generator, depending on what that generator is. If it's rooftop solar, if it's an actual rotating machine, it will contribute a different amount of energy to that fault, right? Solar will contribute very little. If it's contributing very little, it can be hard to figure out the fault is even there. That creates a challenge. Traveling time domain, the idea is it's like dropping a marble into a swimming pool. That disruption, that fault creates a wave that you can see. It doesn't matter what's feeding it. It doesn't matter if it's a solar rooftop on a grocery store or if it's a generation from the grid as a whole. Those waves are there.
Yeah, it's kind of interesting. I always like that analogy is that traditionally the way we've detected faults is something happens on the power system and we wait for the sources to just push as much current as it can. And we measure that's why they call it fault current, right? And in this time domain technology, just you don't care what the sources are. Rather, the fault itself is generating the information that we can measure to know if there's a fault in our particular zone of protection.
But it's super fast.
It's, a millisecond.
You don't have to wait for anything.
No, you always, that's the fun thing, right? The traditional ways, you got to wait for that, 60 hertz power system to push more current at 60 hertz, which is 16 milliseconds. And these traveling waves are moving at the speed of light. It takes us about a millisecond or less to figure out what's going on.
Or you need to wait for side of that power line to get the feedback from the relay that is in the substation. So you don't have to wait for that.
It's interesting. There's some really cool stuff going on. As we look ahead to the future, what are some of the biggest challenges the electric grid will face, and what innovations are on the horizon that get you guys excited?
For me, the number one in the U.S. is wildfire mitigation. I'll put it that way. I think that's something that we have seen in the news recently, and we are investing a lot in our technology to develop a better way to detect those faults and isolate them.
Really hard problem. Very important problem to solve. I agree with you 100%. We got some really smart people taking a new and fresh look at how we can do it.
I think there's a perception concern I have there too. It'd be easy to ask how could this utility allow this to happen, or is anyone paying attention to this problem? What's going on, right? This is one of those, if it were easy to solve, it would be solved. This is a hard problem. It's taking work. There's tons of effort happening around this. It's amazing what is happening, but there's a lot of work still to do.
But the upside is, we tried, for years and years, we've looked at how do we solve this down conductor, these, wildfire mitigation challenges and stuff. And the benefit to us is technology continues to advance. The edge compute we can put in devices, out on a pole, in the middle of nowhere that can do a lot of enhanced signal processing that we were never able to do, say, just 5 years or 10 years ago. Right, applying new statistical methods, I'm not quite sure AI is ready for that, but maybe it is. Maybe we end up, maybe some machine learning kind of things and that we can apply to these particular faults.
Well, and again, maybe it's my automation background, but that right there is what excites me. I have all of this information to look at. I have what feels like an oscilloscope available at any point on the grid I want is the future that I would love to see. What do I do with that? What I do not want to do is stream all that back into one giant hard drive and dump it in all one spot and then try to figure out what to do with it. What can I do with it at the point it's being measured? So that edge compute you're talking about, what can we do that it is not possible to do until you can see the problem? So it's going to be awesome to see what we learn.
The closer you are to the fault, the easier it is to detect.
Absolutely.
All right. This has been a great conversation. I'm going to have you guys back in, 2 years to figure out how good we are at predicting the future. Any parting thoughts on this marvelous electric grid that we're so fortunate to be able to work on and make better?
Well, I've been with SEL for so long and traveled so many different places around the world, Dave. And this is something that we give for granted in the U.S. Every time that we flip the switch, the light's going to go on. This doesn't happen everywhere else. And this is a great benefit of our industry. And I think it's a great opportunity for us to continue delivering systems and help other countries and other utilities in the world to have the same benefit.
Yeah, I mean, I think that's why I like being involved in this as well. We're all working on the same machine here, but it's a machine that impacts literally everyone that uses electricity. And so I can't think of a more meaningful purpose than that. If you're an engineer that's interested in energy of any kind, being able to work on something like this, any part of it it's a privilege, because you're improving the lives of, you, your family, but your kids, your grandkids, your great grandkids. The impact you can have is enormous
on society. I agree with you. Right. Credit to Edge Genius for picking the mission statement of making electric power safer, more reliable, and more economical. Around the world, it is truly impactful and a noble cause.
An easy mission statement to work in.
Yes, sir.
Yep.
Yeah. So if you're a new engineer and you're looking for someone you can create impact, this is the industry to be.
Yep. And apparently everybody needs electricity. Who would have thought?
Right? More every day.
Edison and Insull 145 years ago, I guess. All right, gentlemen. Thank you very much for spending some time with me this afternoon.
Thank you. Pleasure.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.